In this video, we're going to take a look at how to solve circuits with multiple resistors for individual voltages, currents, and resistances, both in series and in parallel. And we'll do so by just taking a look at one of the assignments you have for this unit. So this will act as an answer key for us here. The first thing that we're asked to solve on this question number one is for an individual voltage. If you take a look at the circuit up close here, we are told that there is a certain voltage supplied to the circuit from this battery source or whatever it is of 12 volts. That current then goes through a 4 ohm, 3 ohm, and then 2 ohm resistor before returning to whatever that energy supply is. And these are all wired in series. The current has to go through one, then another, then another. There's no alternate pathways there. So the first question we're asked to figure out here is, what is the voltage supplied to the circuit? That's simply a matter of writing down what's given to us. It's 12 volts. In order to find the current for the circuit, we really need to find the resistance first. So the second and third questions here should probably be inverted. You can't solve Ohm's law, V equals I times R, unless you first know the total resistance. And because these circuits, these resistors on this circuit are wired in series, it's simply a matter of adding them all together. So we have our 2 ohm, 3 ohm, and 4 ohm resistor. Together, they make 9 ohms of total resistance. So I'm going to go ahead and put that in here for our total resistance, and now we can solve for current using Ohm's law up here. 12 volts equals current times 9 ohms of resistance. Gives us a total current in the circuit of 1.33 amps. Those 1.33 amps are the same throughout the entire circuit. Again, we'll take a look at this more closely. If you are supplying 1.33 amps of current out of your battery, that 1.33 is consistent throughout. It does not increase or decrease when it encounters resistors or bare wire. It's like a train that travels at the same speed throughout. So that allows us to make some calculations about individual voltages. The voltage that's experienced over here on what we'll call resistor 1, the 2 ohm resistor, still obeys Ohm's law. It's still subject to the V equals I times R equation, except in this case we're not concerned with the total resistance of 9 ohms. We're only interested in the individual resistance of 2 ohms. So the voltage on this resistor is equal to the current running through the resistor, 1.33 amps, times the resistance of just that individual resistor, which is 2 ohms. So the voltage expressed across resistor 1 is 1.33 times 2, or 2.7-ish. We can solve the other voltage using similar equations. We'll take 1.33 amps times 3 ohms, and then times 4 ohms to solve for voltage 2 and for voltage 3. Voltage 2 comes out at 4 volts, and voltage 3 at 5.3 volts. In problem number 2, we have a similar setup with a known voltage, 25 volts, and individual resistors. This time there are 4 of them, and again they're wired in series. The first thing we're asked to do is figure out the total resistance acting on this circuit, and so again it's really as simple as just adding all of them together. 65 plus 84 plus 73 plus 10 gives us a total resistance here of 232 ohms. So we should take that, put it in as our first answer here, 232 ohms. The current then can be solved, again using Ohm's law. The total voltage, 25 volts, is equal to the current times the total resistance. So we'll write that as 25 volts equals our unknown current times our known resistance. And we divide 25 by 232, we get a pretty small current, which shouldn't be surprising because this is a lot of resistance. It works out to approximately 0.11 amps. The third thing we're asked to solve for is the power. There are lots of different ways to solve power. Current times voltage is probably the most basic approach, and we know current and we know voltage, so we could simply say power is the current, 0.11 amps, times the voltage, 25 volts, which gives us a solution of 2.7 watts. You could use any of the other equations for power, like I squared times R, or V squared over R if you like. You're going to get the same answer, plus or minus a small degree of error for some of the rounding that we had to do to get there. Last thing you're asked to do is solve for the voltage across each of the resistor, and we're asked to label those directly on the diagram. So again, I'll just remind you, when the current comes out of this battery source or whatever it is, it's 0.11 amps, and that does not change at any point throughout the circuit. So each of these individual resistors are experiencing 0.11 amps with slightly different, or in some cases drastically different, resistances. So we're going to go back to V equals I times R. We are solving for voltage, and we know our current in each case is going to be 0.11 amps, and that will be multiplied by whatever the resistances are for each of these numbers. So 10 or 73, 84 or 65. And when we do that, these are the numbers we get. For the resistor at the bottom, 1.1 volts. The resistor over here on the right, 8.03 volts. On the top, 9.24 volts. And on the top left here, 7.15 volts. If you add those four numbers up, you'll find that they do come out very close to 25 volts, which is what we'd expect in a series circuit. It's a good way to double check your answer. Number 3 works out very similarly to numbers 1 and 2, so I'll just provide you with the answers here. The total current is 0.21 amps. The resistance, 38.1 ohms for resistor 1, 4.76 for resistor 2, and 14.3 ohms for resistor number 3. Question 4 starts with parallel circuits. The parallel circuit, we have multiple resistors and multiple pathways that current can follow. So, for example, in this circuit here, current leaving the battery has an option to go through this pathway, the middle pathway, or the pathway that's labeled here on the bottom. In any of those three examples, the current is going to be experiencing a full dose of voltage, getting from negative to positive on the battery. It has to experience whatever, in this case, 4.5 volts. So 4.5 volts this way, 4.5 volts that way, 4.5 volts that way. Each branch, though, has its own resistance, so there's going to be some difference in terms of how that current is split. But that's a fundamental difference between parallel and series circuits, is the manner in which you can figure out voltage and current. So first, in number 4, I'm going to go ahead and label our source of voltage as 4.5 volts so that we remember that here, 4.5 volts. And we are asked to figure out what is the total resistance if you have 3 resistors in parallel, 2, 3, and 4 ohms. The equation for figuring out resistance, total resistance in parallel, is 1 over the total equals 1 over each of the individual resistors, in this case 1 over 2 plus 1 over 3 plus 1 over 4. To solve that, we would first add these three numbers together, and then to get this resistance out of the fraction, the easiest way to do that is to take the inverse of both sides. If we do that, we get a total resistance on this circuit of 0.92 ohms. That will allow us to calculate current. Similarly as before, it's V equals I times R, where R is the total resistance when there's more than one resistor. So we knew that there was 4.5 volts present here. We're looking for the current based on 0.92 ohms of resistance. That gives us a value for the current of 4.89 amps. In order to solve for the current through each of these particular branches, we have to first realize that the amount of voltage on each branch is going to be identical, regardless of the resistor there. Because each of these branches starts at one end of the battery and ends at the other, you're getting your full 4.5 volts as discussed before. So I'm going to start by zooming in a bit on this circuit, and we're going to label each of these resistors with the 4.5 volts of potential difference that they're experiencing. So 4.5 volts here, here, and down here as well. So now that means if we're looking at Ohm's law for each of these resistors, they're still beholden to that law. So voltage is current times resistance. If you have 4.5 volts of electrical potential energy, if you have 2 ohms of resistance, you can solve these using V equals I times R. In this case, individual resistances instead of total. All of these are going to have 4.5 volts. All of them will be solving for current. The difference is that one resistor here will be calculated based off of 2 ohms, one off of 3, and a third off of 4 ohms. And when we do that, we divide voltage by resistance. We get the following currents running through these resistors. Over here on the top, 2.25 amps. In the middle, 1.5 amps. And on the bottom, 1.13 amps, rounded off a bit there. These currents came from our battery initially as one whole 4.89 amps calculated before. And you'll see if you add up these 3 individual currents, they do add up to 4.89 amps because they come from that original stash, if you will, of current. That current, when it approaches the split, sends 2.25 amps toward that resistor. The rest continues down this way. And then there's another split, 1.5 amps of what's left goes there. The other 1.13 continues along the bottom. And then once they meet up again, those currents are additive, so that when you return to the battery, you've got that 4.89 amps of current you started with, just split differently among those resistors. Lastly, here we're asked to calculate the power dissipated by the circuit. This calculation is identical whether you're talking parallel or series, so there's nothing new here. It depends on which variables we want to use, how we want to calculate this, but we could certainly just do power equals current times voltage. That's the total current running through the circuit of 4.89 amps times the voltage across the whole circuit, which is 4.5 volts. That works out to 22 watts. And again, there are some other methods you could use there. It should all get you pretty close to that same number. For the last problem here, let's start by taking a look at what we know. We know the voltage on the circuit overall is 18 volts. We know the current through branch 1 here is 1.2 amps, and we know resistor 2 down here is equal to 6 ohms. First, we're asked to figure out resistance number 1, so we're looking for this guy right here. If we know we've got a parallel circuit here, one thing that we can say for sure is that each branch is going to experience a complete voltage drop from 18 down to 0. So 18 volts across resistor 1, 18 volts across resistor 2, and in fact any pathway that would take us from one end of the battery to the other would experience the complete 18 volts here. So I'm going to go ahead and just throw those numbers in here, 18 volts in both cases. So that allows us to then use Ohm's law relatively simply to calculate R1 in a manner not too unlike what we've been doing all along. V equals I times R, where the voltage is 18, the current is 1.2 amps, and the resistance is what's unknown to us. So 18 divided by 1.2 should give us our value here for R1. That works out to 15 ohms. I'm just going to pull this over and put that in for R1, 15 ohms. Going back to our circuit, I2, the current running through resistor number 2, can be solved in a similar fashion. We've got the same basic approach using Ohm's law to solve V equals I times R, only in this case, while the voltage remains 18, the current becomes unknown, and the resistance is the 6 ohms given to us for resistor number 2. So the current traveling through R2 is 18 over 6, or just 3 amps, running through there. So again, I'm going to go and put that back up here on top so we have that answer. 3 amps, current number 2. The rest of the calculations are all about the total resistance, current, and power in the circuit. So I'm no longer looking at individual items, I'm looking at the overall picture. So let's start by pulling this over again. Finding total resistance in a parallel circuit is using this equation. 1 over RT equals 1 over R plus 1 over R plus however many you got. We just have 2 in this circuit. So 1 over RT is 1 over the 15 ohms that we calculated for R1 plus 1 over the 6 ohms given to us for R2. So you're going to start by just adding those together in your calculator, probably returning a decimal response, which then needs to be inverted so we can flip this 1 over RT around and get the total resistance for the circuit is right around 4.3 ohms. So I'll put that in here as well, 4.3 ohms total resistance. The total current is calculated using Ohm's law from the total resistance. So we'll go again to V equals I times R. 18 volts is the total energy on the circuit. The current is what we're trying to solve. The resistance we just calculated at 4.3 ohms. So we get a total current running through this particular circuit is 4.2 amps. Now we should be able to check that answer by taking a look at some of our individual calculations. 4.2 amps is the amount of current leaving this battery, and it's coming down this branch here, and then it splits into 2 pieces. These 2 pieces, the 1.2 amps and the 3 amps, should combine to make 4.2, and of course they do. 3 plus 1.2 is 4.2. So that satisfies our check of that answer, 4.2 amps from calculation of the total circuit parameters and also from our individual marks as well. That just leaves a calculation of power. We have lots of options for how we might do power since we know both the total current and the total resistance. It probably makes the most sense to stick with the simplest power equation here, which is P equals I times V, where the current 4.2 amps, the voltage is 18, so our power is 4.2 times 18, or 75.3 watts.